Hey everyone, in this video I will walk you through the entire system design of a URL shortener, covering everything from API endpoints and database choices to caching strategies and security measures. We will also address potential bottlenecks and single points of failure for scaling. By then you will understand how it all works, so let's get started. When it comes to functional requirements of a URL shortener, we primarily need two endpoints, one to shorten a given URL and another to redirect users to the original URL. On the non-functional side, the key goals are high availability and low latency. Let's dive deeper into the API endpoints. The first is a post endpoint where users submit a long URL and we respond with a shortened URL along with a status code of 201. The second endpoint handles the GET request for the shorter URL. When a request is received, we look up the corresponding long URL in our database and return it in the location header of the response with the 301 status code. Now let's take a look into the details of creating a short URL system. If we anticipate 1 million URL shortening requests per day and plan to retain them for up to 5 years, we will need storage for about 1.8 billion URLs. Now, to represent these many URLs, we need to determine the appropriate string length for our short URL. If you use 62 readable characters, 26 lowercase, 26 uppercase, and 10 digits, a single character string gives 62 combinations, while a 7 character string provides over 3.5 trillion combinations, far exceeding our requirement. For added security, longer strings can make URLs harder to guess. If the original URL have a maximum size of 2048 characters, storing both the original and its short URL requires about 2055 bytes per record. For 1.8 billion URLs, this totals around 3.6 terabyte of storage. Now, this baseline could increase if we store additional metadata such as creators details, creation timestamps, and expiration dates. Now, here's how the URL shortener endpoint works. It starts by generating a random number between 0 and 3.5 trillion, convert that number to base 62, and checks if it already exists in the database. If it doesn't, the base 62 string and original long URL are stored in the database, and the short URL is returned to the user. If the base 62 string already exists, which is called a collision, the system repeats the process until it finds a unique number. While this method works initially, collisions become more frequent as more numbers are occupied, making it less efficient over time. Now, the second endpoint handles the short URL lookup. When a user accesses a short URL in browser, we search for the corresponding long URL in the database. If it does not exist, we return a 404 not found a response. If it exists, we redirect the user to the long URL. But how does the browser know to redirect? Now, this is where HTTP status codes like 301 or 302 come into play. 301 redirect tells browser to cache the redirection. So future visits to the short URL automatically navigate to the cached long URL without contacting our service. While this improves efficiency, it can limit analytics as we lose the ability to track repeat visits to the short link. On the other hand, 302 redirect ensures the browser doesn't cache the redirection and sends a new request to our service every time. However, 302 isn't as SEO friendly as 301. We can use a 301 permanent redirect for better SEO while preventing caching by including the cache control headers directives like no store, no cache, must revalidate, and max edge equals 0. Now, this approach ensures accurate tracking. Now, in its simplest form, our system design starts with a web server running the application to handle requests for both endpoints, with the web server communicating directly with the database. But as traffic to the service grows and availability starts to drop, we can scale by adding more web servers. To ensure traffic is evenly distributed across these servers, we introduce a load balancer, which directs incoming requests to the right server. Using the same logic to generate short URLs introduces the risk of a race condition. Imagine two web servers generating the same short URL for two different long URLs. Now, after checking the database, both might find the short URL doesn't exist and proceed to insert their record simultaneously, causing a conflict. Now, the simplest way to avoid this is by adding a unique constraint on the short URL in the database and handling any exception caused by conflicts in the application, essentially retrying with a new random ID. But there is another challenge with randomly generating IDs, and it's the collision problem. As more IDs are occupied, collisions become more frequent, making the process less efficient. A better solution is using a counter-based approach, which not only avoids these issues but also scales efficiently as the system grows. But the trade-off here is that the short URLs will no longer be random. To handle counting more efficiently, we can set up a dedicated service for this using something like Redis increment command to get the next incremented number. However, this creates a single point of failure, and as traffic grows, it can become a bottleneck, reducing the overall latency of our service. Using a Redis cluster doesn't fully solve this because a specific counter key will always be routed to the same Redis node, as Redis clusters manage one key per node. At this stage, we need to switch to a range allocation strategy. Here, how it works. When a web server starts up, it's assigned a unique range of number and it keeps track of counters within that range. No two web servers share the same range, and when a server exhausts its range, it requests a new one. So now instead of using INCR, we use INCR by, which lets us allocate a large chunk of numbers like 1000, yeah, 100k, or even a million. This drastically reduces the load on Redis with fewer calls needed for each allocation. We still only have single Redis server. To address this single point of failure issue, we can implement a partitioned key scheme. Now this means splitting the counter workload across multiple Redis keys stored on different nodes in the cluster. When web server start, half can use one key and the other half can use another. Now if one Redis node fails, the remaining server will still handle request using the other key. Alternatively, you can use tools like Zookeeper for even more robust coordination and fault tolerance. Now let's talk about the database. With roughly 2 billion rows to handle, our traditional relational database might struggle with performance. While we could optimize it for querying and use sharding for scalability, a better option would be to switch to a NoSQL solution like Cassandra. Now, systems like Cassandra are designed to scale horizontally, unlike relational databases, which were initially built to run on a single server. As traffic grows, we can handle the increased load by simply adding more nodes to Cassandra. The trade-off, however, is that the system won't be immediately consistent. It will take a few milliseconds or seconds for changes to replicate across nodes. But this approach can support millions of active users and scale efficiently as needed. To further reduce the load on the database, especially for read-heavy operations, we can use caching. Redis is a great choice for this, but should we use the same Redis server we used for counting? Probably not. It's better to keep them separate to prevent counter key evictions. Here, we can follow the 80-20 rule, caching 20% of the most frequently accessed URLs by using an LRU eviction policy. Now, we ensure the cache stays efficient by storing only the most relevant data. For any cache misses, we fetch the data from the database and then write it to the cache for future requests. All right, now that we have got the basics of our system set up, let's talk about tracking analytics, like how many times a specific short URL has been used. Here's the thing, we don't want tracking to slow down the system. So instead of cramming everything into web servers, we are going to build a separate analytics service. Here's how it works. Before we send the redirect response back to the user, we will push a little message into the message queue like Kafka or RabbitMQ. Then the analytics service will grab those messages from the queue and process them. This way, tracking doesn't interfere with the speed of our main system. Now let's talk about the some important daily tasks we should be running to keep things smooth. First, backing up our storage servers at least once a day to something like AWS S3 is a must. It's a simple step that can be a lifesaver for disaster recovery. Then there is cleaning up expired records in the database. This not only keeps things organized but also helps cut down on storage cost. A great way to handle this is by running a dedicated service during non-peak hours to remove expired URLs. Now let's talk about security, specifically rate limiting traffic to protect against DDoS attacks and malicious users. Rate limiting helps us control how much traffic a client can send. To identify clients for rate limiting, we can use few key factors: the API developer key for registered clients, the HTTP cookie for anonymous users, and of course the client's IP address. And that's the system design of a URL shortener. Remember, scaling any system is an iterative process. You will encounter bottlenecks and single points of failure along the way, and the key is to address them as they come. This is just one way to approach the design of a URL shortener. But I'd love to hear your ideas. Let me know how you would have solved it in the comments. Thanks for watching, and I will see you in the next one.